with this presentation, I would like to basically introduce you in some of the parts of the microscope who are important for our workshop. Okay, so, well, we all know that microscopy is really, really good because to explore biology, to study biology, because we can cover certainly a great range of different scale in terms of sizes. So we can go from from millimeter to centimeter in some of the mesoscope microscope that we can have today, to at the level of the single molecule, to few nanometers nowadays. For achieve that goal, we have basically a really a long list of different approaches that we will cover, most of them across the workshop. And they basically, all of them were tuned in different ways. But to make a summary between the resolutions, we can say that wide field and confocal microscope can cover from millimeter to hundreds of nanometers. And this limit in the barrier of resolution was broken with the super resolution. And on Wednesday, we will have 3 experts in the field giving all the details about how they did it and how they are pushing these frontiers day and day. So to begin, so give me a second. Okay, to begin, the thing is, well, we have epifluorescent microscope, and the epifluorescent microscope is not other thing that a lamp, so a light. Then we have here a band pass filter. We will cover this later on, who select the excitation wavelength, and then an objective that will focus our light in the specimen. The fluorescent will be anisotropic, and we will pick part of the fluorescent with our lenses, with our objective. And then a dichroic mirror will reflect the excitation light and allow to pass the emission light. After the dichroic mirror, we will have another bandpass filter which will select our wavelength of detection, right? And then we will have a detector, either our eyes or a camera. This is a regular or a simple epifluorescent, and this is exactly what we have here. So the excitation, the dichroic mirror, our lens for the focus of the light, and then our detector. Something that come up here is that we will focus many different level, many different focal plane, and we will see all of them in the camera, which basically distort or blur our vision of the sample. To tackle this issue, basically the confocal microscopy enabled us to have different focal planes, and this is done by the inclusion of a pinhole on front of our detector. And this pinhole is a little hole who we can change the size, and it will reject whatever is out of focus of the region we would like to see in our sample. This little thing changed basically all the perspective and enable us to do CT stack, 3D volume, and many other things. It will be very important for tomorrow because this volume is finite. So it's the point spread function. And this point spread function is needed for the fluctuation experiment because we need to know where the molecule can in and out. In the next slide, I'm going to explain also another way to have confocal without pinhole. This is basically the same that happened when we use this kind. I find this very interesting in that this kind of glasses that are used for myopia and anti-fatigue, because you got pinhole in front of you, and you release a lot of light, and these are very good because you don't tire your eyes watching a lot of light that you don't need, right? You focus just in what you want to do. So this is exactly the same logic. So what we can do basically with the different approaches is, well, we can do laser scanning microscopy or confocal microscopy, and we can collect different focal plane in comparison with the wide field microscopy, where we have the whole cell. And you can see here how change, the resolution between confocal and wide field. But also we can have spinning disk, and we will see later on how this is implemented. And also we have multiphoton, TIRF microscopy, and many others that can improve the signal to noise. So in the 2004, three guys got the Nobel Prize for the super resolution, who enabled to break the diffraction limit. And there are different kinds. I will not cover today because, as I said before, Wednesday, Fernando Stefani, Luca Lanzano, and Giuseppe Vici-Domini will cover in detail all the different approximations, as well the new things that they are doing. But what we need for a laser scan microscopy? Well, we need, first of all, we need our source of light that can be, lasers. We need something to move our light, because in comparison with the fluorescent that we illuminate all our focal plane with the light, now we need to move our beam across our specimen. And this is done by scanner. We will see different kind of scanner. Also, we will need detectors. We need to collect. And we will see if we will use single point detector or parallel detectors, and we will one and another. And also we will cover some details about optics, electronics, and the new adaptive optics for improving the resolution. So in the market, there are several kind of different lasers. Helium neon are the most common, and argon are the most common. But today, the diode laser and the diode pump solid state laser are very, very common, and they really revolution, because they reduce a lot the price, and we have all the wavelength that we want. But all these lasers are continuous. These are not pulsing. And for lifetime measurement, we need pulsing. We need a pulse, and then a window, and another pulse, because within the pulse and pulse, we will collect our photons. So what we can use for film? Well, first of all, there is a group of lasers which are known as supercontinuum lasers. And this white laser contain basically wavelengths from above 360, 400 to 1 micron or even more. This is up to 2 micron. And we have all wavelength and a really high power. This is by default modulated at 20 megahertz, which basically give you the chance to collect photon between pulse and pulse. One disadvantage or advantage, depending on how you look at the technologies, well, you will need to use bandpass filter to select the region of excitation you want to use, because they are all blend. But also you can co-excite many. And I know that Lorenzo Scipioni is going to talk about a particular microscope that he developed for spectral and lifetime film, spectral and film. And he's using one of these supercontinuum laser, and he has all the wavelength, and he can do everything he wants. Even he's also considering to use the laser. The laser that he got is really, really powerful, and he can also use for STED. So he can deplete in the excited state and going down to the dark state. But also we've got other kind of laser who are pulses, and these are multiphoton laser. Most of multiphoton laser by default are 80 megahertz, but this is not the only one wavelength. And this laser has a pulse of 100 femtosecond, and we will see in a minute that this is very important to produce the photon excitation. And they cover a really broad range of wavelength from 680 to 1000 or 1100, something like that. And also a really long range of power. These lasers are really, really powerful. And here I represent 4 examples. There are many more. And I highlight these 2 because these 2 are the ones that we got here. One physics, a MITI with the deep sea model, which is for, and we will see later on that this is important for avoid distortion of the pulse when the pulse is going through the optics. And also we got a fiber base with a single wavelength, which is from Carmel. This is from Carmel. Is from Colmar. Colmar is the brand of this. And in comparison to this 30 megahertz, this is a 50 megahertz. We have a longer window between pulses. These are very useful, not only because we can penetrate deep in the sample, but also to do lifetime. And nowadays there are some of these lasers has extended range. And for example, this from coherent and this from spectral physics can go up to 1.3 microns, so 1,300 nanometers, which open a room for an area which is 3-photon excitation instead of 2-photon excitation. Well, but what is special about the 2-photon excitation? And I will try to go fast with this, but it's something that is important to cover. So, well, if you go to and you read Wikipedia, it's really hard to understand what is going on with photon excitation, because what they say is, well, it's strictly speaking true, but difficult to understand. They say 2-photon excitation concept is based on the idea that absorption of 2 photons of the half of the energy need for 1-photon excitation. This is true, and can excite a fluorophore with as a 1-photon event. The 2-photon also depend on a quadratic function of the light intensity, and for instance, is not linear. Okay, so let's come back to the basics and see what this means and what we need to do 2-photon excitation. So as Enrico introduced in the Perrin-Jablonski diagram, if we have a molecule in ground state and we we focus the light with the proper excitation, we will excite, and after some reorganization in the excited state, it will emit at longer wavelength. In the 2-photon excitation, what happens is we need to excite with 2 photons of the half of the energy. So if this is 400, for instance, this should be 800. So 2 photons of 800 will do the same, and will reach the same excitation level. And then after some reorganization, it will fluoresce in the same properties that a single photon. For me, it was still dark to understand how this happened. And a person explained one that the time is what matters. And when you understand that time is what really matters, I think it's more clear. Well, if you understand that for excitation of 2 photons, we need femtosecond time, well, this match with the growth of the pulse that we have in 2 photons. Our pulse broadening is on the 100 or less of 100 femtoseconds. So we really compress of the photon in a time scale. And this is one of the important points. And the other important point is to concentrate that energy. And this is spatial compression in the next. So the thing is, you have a bright day. Basically, you can excite a photon per second in a single photon excitation. If you wait 1 to the 10 million years, you will get 2 photon excitation. So basically, we need to do something otherwise this is not a useful technique. So we deserve all this theory to Maria Goppenmeyer, Nobel Prize in 1963. And she did all the theoretical calculation. And I will not go into the details of the formula, but the important thing is the cross-sectional excitation, which talk about the excitation in the 2 photon range is proportional, is a probability proportional to the inverse of the frequency square, the power of 2 of the frequency and the pulse duration. And this is the important thing, and is proportional to the power of 2 of the average power that we apply. So in a continuous laser, we have many photons coming with a constant intensity. However, in the pulse laser, we compress all the pulses in discrete amount. So the temporal compression of the photon is important. Then we use optic in order to compress basically the photon in space. So we concentrate all our photon and pulses in a spot, which is the. So when we talk about, we always intrinsically speak of confocal microscopy. So we don't need a beam into photon excitation. And why is cool and why we can compare two photon with one photon? Well, the first thing is, well, we can penetrate more in the tissue. And why? Why we can penetrate more? Well, the first reason is because the scattering depends on the inverse of the power of 4 of the wavelength. And you can see here the coefficient, the scattering coefficient here going down along excitation goes higher. And this, I want to make a point here. This is a logarithmic scale. It's really changing a lot. And also, there is less absorption in the infrared region because hemoglobin and water does not absorb too much light in this window. So basically, the reason for why we can penetrate more are these two. The other important thing is the illumination has not autofocus. And you can see here in this example, this is a single photon excitation, and you will see here the cone of illumination. And here you have two photon excitation at this point. There is no excitation before or after the point where we are focused our light, which this is useful because this decrease photo bleaching and this decrease photo damage of our sample. Okay. So next step is moving our beam. To move in our beam, we need basically a scanner. And there are many different approaches, and we will talk basically most focus on confocal and super resolution, which is used the same, and also multiphoton. And we will see a particular configuration of scanning and collecting the data for two photon that is not possible in a confocal, and increase the sensitivity of the photon detector. So the scanning unit is basically a set of two mirrors that can move one horizontal and one vertical our beam. And using the scanning optics, so scanning lens and tube lens, we can scan across our sample. There are different kinds of scanners. In particular, the most used scanner are galvanometrics. These are, we will see in a minute, but very precise, quite fast. And they are really very reproducible in the dwell time, so the time that we spend in each of the points. The resonance scanner has a frequency of resonance and is fixed. They are very, very fast, but they are not that accurate in the repetition, in the ramp of scanning across the image as the galvanometric. And this will be important, for example, for the RIGS, the NMB, and many of the fluctuation experiments, because if you have changes along the scan in the time, right, along the scan in your image, and you cannot calibrate because you are not reproducible, you cannot do fluctuation in space. And there are some other ones, like a polygon scanner. I never saw one in use. And there are also the acoustical deflector, and these are very useful because we use it for attenuation, because this is a crystal that we can apply, and this will vibrate. It will produce vibration in our crystal and will deflect the light, and we can use it not only for attenuation, but also to move our beam. Nowadays, at the end, I will talk about adaptive optics, which can be used also for scanning, and it's very, very useful. So the other way, not using a scanner, is moving your sample, because if you have a spot and your spot is confocal and you have a stage, you can explore whatever you have and you can make an image. It is very slow, but you can make an image. And there are piezo stations who are very precise and quite fast that you can use it. The problem is, well, it is slow, but it's very, very precise. You can really move piezo stations with, I will say nanometer or sub-nanometer resolution, because in the CT stack for orbital tracking, we will see Wednesday with Enrico presentation that you can really follow a molecule with a resolution of a nanometer. Speaking about the configuration of how we use the scanning and the detection. So for a confocal microscopy and also for 2P excitation, when I speak about confocal, I also speak about some of the super resolution microscopy. Well, we have our laser, and then we basically have here a dichrom mirror. This dichrom mirror will reflect our excitation and will allow to pass the fluorescence. So if we put the scanner between our basically scanning optics and this dichrom mirror, when the fluorescence came back from our sample, it is quiet. It is collimated and it's not moving. And we can easily focus in one or two detectors, depending on how many wavelengths we want to collect. And this is known as the scan configuration. So the light go through the two mirrors, then the scanning lens, the tube lens, and our sample. And the fluorescence came back, pass through to the dichrom mirrors, and then to our detector. In our case here, we have another dichrom mirror with two bandpass filters and our detectors who are here. These are basically the configuration of all our confocal microscope in the lab. But if you have a photon microscope, you can use another strategy, which is non-descan. And what this means? Non-descan means that we can pass our laser through the scanner, but we can place our dichrom mirror to split between excitation and emission after or in between the scanning optic and the scanners. What happens if we do that? Well, we save a lot of photons of the fluorescent that are reflected in each of the steps that we have in all these optics. So every optics, regardless of how quality it is, it will reflect some of the light, and we will lose some of the photons reflected. So if you do this, basically many of these, and you will focus all your light in your detector. Well, there is one important thing here. Well, you need to have a confocal volume here, and the only way to do it is into photon configuration, because the beam here is moving, so you cannot pass your beam through your pinhole, because it will be always moving across your specimen. So you need to do basically put your optics here to focus all your light in your detector, and that's it. Many people use if you have a really weak sample, or if you want to use all the photons that you want. Your thing. Okay, so as a summary, laser scanning confocal can be, really fast, high quality, high resolution, and the frame rate can be kind of slow. But there is another confocal microscope, like the spinning disc, which use this wheel with many pinhole, fixed pinhole, that is moving on top or after your objective, and it will basically, using a lenses, you will make a pass the light for different region in space here through the pinhole, and will select a region of interest. This is poor in the resolution, in C resolution, that a confocal microscope, because this is fixed. But you will read all the pixels parallel with a camera. So you are really going to go really fast, because in the scanner we can detect a point in a microsecond time scale, and here we can go maybe to the millisecond time scale, but a million of pixels in parallel. Okay, so we need detectors, we say. Oh, well, for point detector, we have basically two big areas: the photomultipliers that can be built of different surfaces that can detect photons with different range. And here is a plot that shows the sensitivity to wavelength for the different surfaces of the PMTs. And nowadays, one of the best one are these gallium arsenate phosphodiene, which are really high in quantum yield. So the number of photons detected by the number of photons heated in the actuator. And also it has really nice range of detection from 400 to 650 or 700. And then we have avalanche photodiode. The main difference between this and this is the output in this is analog, and the output in this one is digital. And this is important for the experiment that we will learn tomorrow on the fluctuation, because we need to calibrate our analog detector to count one photon, one molecule, one photon, one molecule, right? To count single molecule events. These are also very, very broad in the range of detection, and it has really, really high quantum efficiency, really, really high quantum efficiency. So let's see how this works. Well, in the PMT, in the photocathode, we have basically a surface where the photon will hit, and after there is a photon that hit our sample, it will produce basically a photoelectron, and we will have dynas, indeed 8, before the anode. And there is a power placed one after another, a delta power placed at one after another, that will increase the number of photoelectron release after one after another. So it's basically a cascade that usually involve, for one photoelectron between 4 or 5, but can be more. So for one photon, you will end up having 6,000 photoelectrons. So you really amplify quite a lot. But the problem is you also, for the power that you are applying, you also increase a lot the noise. And this is basically a problem if you increase a lot the gain between the photocathode and photoanode. There are different configurations. This configuration of one side or basically hand-on photomultiplier depend on the application that you use. But the most important thing for us is the response is in the nanosecond time scale. This is how fast they respond to the signal. And also we can read them really, really fast. So in the gigahertz time scale, which means that we can, count a lot of information over the time. And this is fundamental for film measurement, because we will need to have many, many windows over the time, and we need to collect the photons at the proper time in our detection. So then we have we got avalanche photodiode, and the avalanche photodiode is different. We have a depletion region, and then two areas. One is dope, is known as a positive dope or negative dope region. And then if we basically change the potential between these 2 points, we can increase or decrease, the number of release photoelectron by photon hit the active area. This is really, really useful because it has a lower dark current, so noise, for a long range of fault. You will start to see a problem, for very high. It's flat basically in all this region between 500 to 200 volts, which really give you the chance to count single photons. And this is by default, digital signal. Nowadays, there are combination of, sorry, this thing is bothering me. Okay. There are, different combination of, detection by photoelectrons, by hybrid detector, in which we can have an APD as well as a PMT together. And these are very useful today for the film measurement, because you can really read really fast, and it has a very high quantum efficiency. And also they are very low in after pulsing, which is an issue for the fluctuation experiment. Okay, then we got cameras, and with the cameras we have a really large amount of them. So CCDs, charge couplet detector, or EMCCDs, which is electron multiplication of CCDs, or CMOS. And then we got intensifier CCDs for film, or even CMOS for film. And I think Enrico will talk about camera film and film tomorrow. But also we got nowadays some new detectors that can be used as a cameras. For instance, in the new configuration of the size LSM 880 and 980, they use an array of 32 channel, which is here, the ID detector, which is indeed a camera, right? You basically are imaging your PSF, and without using a pinhole, you can basically get information of the distribution of your PSF, fit, and increase the resolution. But at the LFT, they use it as a camera, and they can do correlation between the actuators and do basically all the part correlation experiment that Enrico is going to talk today. And also there are avalanche photodiode arrays that are used for the same purpose. And on Wednesday, Giuseppe Vicitomi is going to talk about his application of the avalanche photodiode array for fluctuation and film. And there are many different configurations, like square or the linear PMTs that can be used for spectral imaging and many more. So how work and what are the difference between the CCD, so charge coupled device, or the CMOS device? Well, in the CCD, basically we have our actuators, and then we will read line by line, one after another, because we got basically independently information in each of them, and then it's transferred to the readout, and then is basically done the amplification and conversion to digital signal one by one. This is important because in this case, this is one of the bottleneck on the reading of the information from the camera, because you need to wait. You need to wait until you read the information from the pixel ahead to read the information of the pixel before. But the advantage is that basically all the amplification is done with the same calibration. So the signal to noise is equal for all the pixels in the camera. On the CMOS, the technology is different because we have amplified and condition our sample, our signal in each of the actuators. So we read our lines, but we don't need to amplify. It's already amplified. So we can read really fast. And we can see here some of the comparison. While chips are similar, we can include many more pixels in the CMOS in comparison with the CCDs. They got quite similar quantum yield, but we can read really wide fast in the CMOS versus the CCD. And the comparison in signal to noise is kind of similar. And here are basically the comparison of the two different cameras. Nowadays, there are some new technologies that is known as a back illuminated, and this really changed the game because we can do really single molecule experiment with CMOS, reading a really fast rate. And I think during the super resolution, some of the speaker will explain which camera they use and why they use. And finally, we got basically the electron multiplier. Basically, on top of the CMOS detection, what we got in the electron multiplier is a series of high voltage amplification that increase the signal to noise over and over, usually over 4 steps, that amplify our output, increasing the resolution quite a lot. So for instance, here is the comparison between the 3, and you can see how sharp is this image in comparison to the others. This is slow. For this reading, if you want to go fast, you need to do crops or binning, which the basically the problem of losing resolution. With the CMOS, we have rolling shutter because we read line by line. So we can go fast by selecting a region of the chip of reading, but we don't need to do actually a crop of the whole chip. Basically, we can read a series of lines in parallel and we will go faster. But these cameras are fundamental for single molecule and basically for all the super resolution, either the new CCDs, scientific CMOS, or the EMCCDs are the detector for super resolution. Then we need electronics and some other parts. And we will basically cover a little bit of electronic for detection, electronic for moving scanner, make the detection digital, and then some other optics for make the system work. So for those of you who will like, later on we can visit the lab and I will show you basically all this electronic because we are in the process of building one of our microscope, and I just finished of the box that has the drivers that control our scanner. And to give direction to our driver, basically we need another car, which we use an IoTech car, but there are many different brands that give you the voltage to the driver to move the scanner in one direction or another. And we custom build this, and it's basically the fundamental part to move our scanner in any possible direction. Most of the brands use this same configuration, and often we have only point detection, line detection, or basically different range of square or rectangle. In our setup, we can move our scanner as we want. Even we can do circular, or we can do any kind of shape. And this will be very important for the object tracking on Wednesday. And Enrico will explain a little bit more on that, because we can do whatever function we want, and we can provide the information to the scanner to do this. Then we need to collect our photon after they came out from the detector, and we can use for for regular detection, so analog detection, the IoTech, or we can use FCS card, FLIM cards, time correlated single photon counting card, which are for FLIM measurements or lifetime measurement. And nowadays, there are companies who are pushing with the FPGA for parallelizing as many channels as we want. And in particular, FLIM Labs, which is an initiative and startup from Alessandro Rosetta in Italy, is now offering this FPGA, and it's the card that we got for a second microscope we are building in the Institut Pasteur, the diver, in which we will have 6 parallel channels. But then when the information came to the card, before the information came to the card, we need to condition it. And we need an discriminator, which is, first of all, we need a preamplifier, we need amplifier the signal, and the discriminator will tell to the card if the signal is one or not, is digital or not. And this is just some electronics that you need to calibrate, and then it works. And in this project that Lorenzo will tell, I think tomorrow, this is the discriminator and amplification for 32 channels in parallel. So he can achieve basically FLIM in 32 channels, so spectral FLIM, truly parallel spectral FLIM. So in the last, I think 2 or 3 slides, I will cover what we need to split fluorescent from excitation. So, well, we will need filters and dichromatic mirrors. And dichromatic mirrors are needed because we need to use in the, reflects or allow to pass through the light from our sample. And this can be short pass filter or long pass filter, or dichromatic beam splitter. We can even have, dichromatic mirror with several bands, so we can select ones. Or we can have interference filter, in which after deposit different layers of materials, we can interfere and have very sharp bandpass filters. For a particular application, one of the restrictions of the interference filter is that the photon need to hit at certain angle. So for instance, if you have a micromirror, it is intended to be used at 45 degrees. If you put on any other angle, it will work, but it will compromise the performance. So in the interference filter, most of the time it works at 0 angle. So it needs to be perpendicular to the beam. If we tilt the angle, it will have a problem. This will be a problem when our photons are scattering, are not basically collimated, are not all coherent. So this happens when we have fluorescence coming from a high scatter sample. If we use our optic, usually we make the light again coherent and we can handle with this. But we will see on Wednesday a particular instrument which is called diver, which use color glass filter, because in this case, the photon will be absorbed at certain wavelength and will not be absorbed certain and some others, and this will transmit this light. And these photons, these filters are very, very useful for this, because we can collect photon under not parallel or collimated condition. Okay, so finally, my last slide is basically about adaptive optics mirrors. And I wanted to highlight this today because I think Wednesday, when Sasha Alexander Dvornikov will talk about diver, he will explain in detail. But problem that we have when we focus light through our optics and they get through in a tissue with inhomogeneities in the index of refraction is that the photons that are coming on different spatial, location in our beam will diverge and will focus on different point on our point spread function, which is highlighted here. You see in the top of this line, you see that on top we have a very, sharp resolution. And even when in the bottom we have a very high count of photon, the resolution is very, very bad because the point spread function is getting very, very broad and we cannot resolve in space our sample. And this is due basically this situation. But if we can have an optics that can correct or pre-compensate our beam in order to modify our what we call wavefront, so it's the front of the photons coming, we can basically tackle this issue. And this is what adaptive optics does. Basically, adaptive optics is not other thing than an array of many, many small mirrors that can be moved independently in all the axes. So we can reshape our wavefront in order to get the best resolution at the depth that we got. And I just want to show basically here, that in this image of a brain at 2 millimeter, we can still get information with the adaptive optic on, and we cannot see anything without adaptive optics. And I think Wednesday, Sasha will explain in more detail. So this is all that I have. I just want to cover basically the instrumentation we got in Uruguay. Basically, we have many commercial microscopes, all of them confocal microscope, and some epifluorescent. And in the advanced bioimaging unit, we are developing 2 custom built, one 2P with the with this single wavelength excitation fiber base, and another 2P, which is the diver microscope, which is connected to this tunable 2P from spectral physics. And this is a wonderful instrument for deep tissue imaging and intravital imaging. So I want to thank all of you for the attention and